Today, cast in a stronger role, it takes its place in daily life and touches us all in some way from dawn to dusk, from communication to sanitation, so to speak. Logically, cast iron was the natural choice of the early designers, including boilers for heating. Thousands of ideal boilers still in use today, like this 20-year-old stalwart, are still going strong and prove the point. Cast iron, hard work, long life. Throughout the world, time-mellowed and familiar skylines are changing. For as land prices soar, vertical development is the only logical answer. Even the enduring beauty of Wren is sometimes shadowed by the conquest of overcrowded space. The problem of space heating becomes acute as buildings grow taller and taller. The heart of any system of heating is its boiler and the metal of which it is made. Two metals are in general use, mild steel and grey iron, but neither possesses all the ideal requirements. Even in high buildings, the consultant engineer would doubtless prefer to use cast iron boilers for all their advantages. But the limitation of cast iron rules against it. It can only be used for buildings of modest height. Water pressure is a natural force which has to be reckoned with, whether created by nature and unharnessed, or generated in the service of man. Rising head, rising costs. But let's tell you about the spectacular resolution to the problem. Boilers made from spheroidal graphite iron, a technique of so treating cast iron as to bring to it a new strength and flexibility, and the power to serve buildings of contemporary height. To see why, let's visit the laboratory. The metallurgist is setting up a polished sample of normal grey cast iron. The spidery lines are the flakes of graphite, an element which is always present in cast iron and which gives to the metal some of its well-known advantageous characteristics. Graphite in flake form limits the tensile strength of the metal and restricts its use. The metallurgist changes to a polished sample of spheroidal graphite cast iron. Now you see that the graphite has taken the form of well-defined, evenly distributed spheroids. This change trebles the tensile strength of the metal. Engineers in many industries have been quick to realize that in its various forms, SG iron can solve many of their problems. For example, the wear and tear placed on the track rollers of excavators of this size was tremendous, and conventional metals couldn't stand up to the load. When SG iron rollers were fitted, they proved entirely up to the job. Within a short time, SG iron has become the logical choice of many designers when complex components are required of a strength previously obtained only by forgings, steel castings, or by complex fabrications. Today, SG iron is established as a modern engineering material. We have then a metal which has all the virtues of cast iron, with its high resistance to corrosion, plus ductility, strength, elasticity. These were the factors which led Ideal Standard to start a research program into the suitability of SG iron for making sectional boilers. The program ranged over many facets of the material, both chemical and metallurgical, as the flow of pilot samples from the foundry got underway. In a remarkably short space of time, the intermediate reports from many departments were ready for evaluation by the metallurgists, and at first sight, the results looked more than promising. After further investigation into every conceivable hazard, for this was a breakthrough project, it was proved beyond doubt that the new iron possessed not only all the good and lasting characteristics of the old, but that mechanically its properties were akin to those of steel, and it would be entirely satisfactory for the production of large sectional heating boilers. Soon production techniques were stabilized, and the manufacture of SG iron boilers began. The essential factor in the production of high-quality SG iron is the scientific control at all stages, starting with a vigorous vetting of the raw materials. The greatest bulk in the charge is pig iron of known analysis and of the highest quality, which is accurately weighed before being charged to the furnace. To this is added offcuts of deep drawing quality steel, also of known analysis. The makeup of the charge required to give the desired final analysis is carefully calculated. The furnace man is at all times under the guidance and direction of the metallurgist. The mains frequency induction furnace has been run up, and a start is made by melting the pig iron. Ferrosilicon additions are important. Its purpose is to provide a nucleus for the graphite. The quantity must be exact. To the now molten pig iron, as the temperature builds up, the steel is added, but some time must elapse before the higher temperatures required for the successful manufacture of SG iron are reached. While the furnace is reaching pouring temperature, the molds are being made in the foundry. Ideal Standard have been making sectional boilers for a long time, and producing molds for SG iron casting presented few problems. Following conventional techniques, the molds are made stage by stage, from the first application of the facing sand to the high-speed filling of the molding boxes by mechanized methods. When the rammed and compacted molds have been stripped from the patterns, they are transported to a conveyor line and made ready for pouring. At the furnace, an almost clinical atmosphere is established, for this is the critical time, as the metal temperature approaches pouring heat. The preheated pouring ladle is made ready for the treatment of the metal with magnesium. The magnesium nickel alloy is placed in the bottom of the ladle and covered with steel plates to prevent premature ignition. The metal is now ready, the temperature correct, and the signal is given for the furnace to tilt and for the treatment to commence. Treatment that will result in the production of high-quality spheroidal graphite iron. The white flare is spectacular as the molten metal strikes the magnesium. Residual amounts of metallic magnesium remain in the metal, and the graphite forms into well-defined spheroids. These spheroids, evenly distributed throughout the matrix, give the metal its high-strength characteristics. After some manual puddling, a late inoculation of ferrosilicon is added. The metal, so carefully prepared and of known and accurate analysis, is ready for pouring into the waiting mold. Constant monitoring of temperature at every stage of the process is extremely important, as the furnace charge is checked before the next pour. Every stage of the process is recorded and samples taken for stage analysis. Now the foundry men come into the SG iron picture, as the metal is transported from the furnace to the pouring stations. The first rush of metal into the runner box is arrested so that clean molten metal can rapidly fill the mold cavity. After pouring, the runner heads are knocked off and the casting will remain in the mold until down to room temperature. This controlled loss of heat ensures a full annealing of the casting and the maximum ductility of the metal from which it is made. When fully cooled, the casting is shaken out of the mold, and the 3 test pieces which were poured at the same time and under the same conditions as the boiler section are sent to the laboratory for a bending test to establish the ductility of the metal before the casting leaves the foundry. A small sample is polished and the microstructure is carefully checked. Now, a test piece is accurately turned and checked on the tensometer to establish that the strength is to the required standard. If the tests fall short of the standard, the casting is rejected. A birth certificate is created for every section so that its history is available for all time. In the physical laboratories at Priestman Brothers, the well-known manufacturers of excavators, Ideal Standard is a further control of quality, periodically have the metal tested for strength. An accurately machined test bar is set up on the Denison machine, force is applied and the bar comes under tension. When the needle reaches 0, the limit of elasticity is reached and the reading taken. The extensometer is removed from the specimen and then a further load is applied until the metal fractures. The reading on the machine, 10 tons, is the equivalent of 40 tons per square inch. The fracture specimen is reassembled in the clamp. Notice the degree of stretch which has taken place between the standard markings. Whilst in the laboratory, let's see a similar test carried out on a mild steel specimen. Once again, the load is applied, the limit of elasticity reached, and then the specimen will be tested to destruction. The machine registers 8.5 tons, the equivalent of 34 tons per square inch tensile. Let's look at the results of these tests again in diagram form. You will see that the strength and characteristics of SG iron compare more than favorably with those of mild steel. Spheroidal graphite iron, ultimate strength 40 tons per square inch. Mild steel, ultimate strength 34 tons per square inch. Spheroidal graphite iron, yield strength 24 tons per square inch. Steel, yield strength 20 tons per square inch. Elongation 10%, elongation 27%. Bending tests of the same two materials also show similar characteristics. Firstly, mild steel, which, as you would expect, is fully ductile. Now, SG iron, almost identical. SG iron has mechanical properties very similar to mild steel. And, vitally important, it has the overriding advantage of far greater resistance to corrosion. Let's return to the production of SG iron boiler sections. They're produced on a flow basis. Here the runner bar is removed by high-speed carborundum saws, leaving the casting ready for its first pressure test. After testing, the casting moves on to the high-speed grinding machines where the section beads are accurately ground, thus ensuring gas-tight joints between the sections on the final assembly. When fully machined and before being finally accepted into stock, every section is subjected to a prolonged water test at high pressure, equal to a static head of 700 feet. The results of these last tests are also recorded, and the birth certificate is filed. A thorough testing to ensure adequate safety margins is the ruling force in all high-pressure components. A random sample is chosen for supranormal testing. Under a protective steel net, the pressure in the boiler section is increased to a remarkable 1,300 pounds per square inch, or 3,000 feet of head pressure. This enormous overload can be maintained indefinitely, the SG iron casting remaining intact and unstrained. As an indication of SG iron's resistance to impact, we show the effect of a 1.5-ton ball dropping onto a boiler section from a height of 40 feet. The casting does not shatter. This section has been similarly tested 8 times. Another interesting bonus of SG iron is its free machining property. At first sight, the turnings resemble those of steel, but they are, of course, SG iron. Assembly is carried out on site, one of the advantages of sectional construction. This with competitive price, resistance to corrosion, and easy installation and maintenance makes spheroidal graphite iron boilers the obvious choice for use in high buildings. For the engineer and the architect, the introduction of spheroidal graphite iron into the manufacture of the time-tested and proven range of ideal standard sectional boilers is of the greatest significance. The dramatic breakthrough of spheroidal graphite iron has enriched many industries, has overcome problems, and led the way to developments in many fields. Whatever the changing skylines have in store for us, in the basic role of warmth and comfort, from this great 90-acre manufacturing plant, ideal standard point and will point to the way ahead.